yeah, I would like to say something about slow hashing algorithms, about a story of migrating existing password hashes to stronger ones, a successful case study. Maybe first of all, I would like to ask you, by the show of hands, how many of you have heard anything about slow hashing algorithms, for example? Okay, some of you. Okay, and how many of you are professional developers? Okay, a bunch of you. Okay, so I hope that every one of you will have something that will be new and informative from this presentation, I hope. So maybe a little bit about me. In the beginning, my name is Tomasz Borowiec, and I'm a senior software engineer here at Ocado. Senior is just the way the company is wants to acknowledge that I'm old. Agenda of my presentation. Firstly, I would like to introduce you to the topic of slow hashing algorithms. We will take a closer look into a bcrypt hash. I will show you a small live demo of some slow hashing algorithms. I will show you the hash computing times comparison, and then I will switch to the case study. I will guide you through our migration process that we went through, and I will tell you what we start with, why we decided to change, what tools we created and used to perform the migration, and also get through the whole migration plan. And we'll be pretty open about the problems that we had. So and in the end, some summary, some links. Okay, let's start. Hashing algorithms. I think most of you, maybe all of you, know what they are about. Basic things. So we're having this input. It'll be a string. Go through the algorithm. Let it be MD5, for example, and we get some kind of output, like a hash, right? It's a one-way function. We cannot know what was the input. We only know the output. Okay, but if we run through the same input again, we will have the same result. That's the basic concept. Okay, so hashing algorithms are divided into basically, let's say, two groups. First are these fast, old school, and general purpose hashing functions, which I believe you all know. MD5 or SHA-1 are examples of those. And these are very good if you would like to identify something, like, for example, if you use Git for version control, you can identify commits by a SHA-1 hash, or if you download something from the internet, you can check if it's valid by calculating its MD5 sum and comparing it to the one that's shown on the website you've downloaded it from, and then you know that the file is okay, right? And these are fast and general purpose, as I said. And there are also there's also this other group, the second group, slow hashing algorithms, also known as bcrypt and friends. And examples of these are like here, but I'll talk a little bit deeper about them in a second. So why slow hashing algorithms? Okay, what are they for? They're designed to slow attacker down. So what we're actually dealing with here with slow hashing algorithms is a unlikely problem when our database of password hashes leaks somewhere. Someone, some hacker maybe acquired it in some way. So basically, if this event occurs, attacker would try to crack the hashes, try to run through some, I don't know, some example input passwords and see what kind of passwords we have. So these slow caching algorithms have configurable length of computation that we define. And about the unlikeliness of the breach of losing database, I would argue if this is actually unlikely, because as you all know, probably even big guys like Dropbox, LinkedIn, experienced it at some time. So it's something to think about, I think, for sure. What the definition of these provide already is salt. How many of you are familiar with the concept of salting hashes? Okay, a lot of you. So just to make everyone on the same page, salt is some string that we add to every to a hash before actually hashing it. So we receive a password from a user, we add some string, that'll be a random string, and we are computing a hash from it. That prevents us from some so-called rainbow table attack. So if we lose our database of hashes, some attacker, some hacker probably has pre-computed hashes of some passwords already stored, and he can just run through this database and see which hashes are there. So if we have salt for every single password, different salt, then we're protected from this simple attack, and we're influencing the speed with which the attacker will gain the passwords. And also, as I already said, all slow hashing algorithms have something called a cost factor, which we as developers, as users of them, configure. So we have the ability to say that we would like this algorithm to be more costly or less costly, and it is different for every algorithm, but every algorithm has something that can be treated as cost. So now about the examples of the algorithms. The sequence of the algorithms is not random. These are actually exact sequence as OWASP has on their website. So from the most the best to the weakest, although all of them are good enough for you. So all of them are well, and they can protect you. So firstly, Argon 2. Argon 2 is a pretty much a new player. In 2013, there was something called a password hashing competition held by some guys, and a lot of algorithms took part in it. And in 2015, the winner was announced, and it is Argon 2. And this is considered to be the best choice for now. The second algorithm recommended is PBKDF2. It's a very easy name. And it's an acronym, of course, because we're in IT. So it stands for password-based key derivation function 2, because one had bugs. So they created the second one. This actually is an algorithm that has FIPS certification, which is a US government standard. So if you're in a company that produces software for some US government, some IT for US government, then maybe you need this certification. That may be the way to go for you. Another example is Scrypt. So the latter ones actually work on core. So the cost factor is affecting core, while Scrypt has the ability to work on memory. So it's like memory hard algorithm. Because someone decided that cores are relatively cheap now and relatively easy to acquire. So maybe we'll choose something that is more expensive. So they decided to go with memory, and they designed this algorithm to be memory hard. And this is the characteristics. And bcrypt is something that is also well known and is also recommended. And it uses underneath, it uses a blowfish cipher. Basically, what most of the algorithms do is they are what we configure is the number of iterations of hashing that we want this algorithm to do. So for example, for bcrypt, we have we configure the power of 2 of iterations of blowfish cipher. So if we configure bcrypt with the parameter of 5, that means that actually it will do 32, is 2 to the power of 5 iterations of blowfish cipher, and the resulting hash will be hashed this time, this amount of time. So this is this cost factor that we are configuring. Okay, so let's dig a little deeper. Let's see. Let's hash Ocado string with bcrypt. We'll get something like this. So it does look like some gibberish, but it has some elements that have actually some value. This actually is a OpenBSD format of a hash, and it has some elements. First element is version of algorithm. 1 is reserved for MD5. 2 is reserved for bcrypt. We have 2A because 2 had problems. There's also 2X and 2Y. If anyone is interested, good news, there's internet. So I invite you to read a little bit about it. I will not tell you about those, but 2A is a good, let's say, it's a good enough version. Another parameter here is the number of iterations expressed, as I said, as a power of 2. So this says that this hash was computed with a cost factor of 8. That is 2 to the power of 8, which is 256, I think. And yeah, this is this information that is held here. Another thing interesting here is this piece. This is 22 characters of radix 64, which is a slightly modified base 64 encoding of salt. So this is salt encoded in radix 64. And the last part are 31 characters of radix 64, of course, encoded resulting hash. So what happens if we have this kind of hash stored in our database as a user password hash? User provides us with his plain text password. In this example, it will be Ocado. We'll search for, user also, of course, provides some kind of a login that we can identify them with. We search the database for this hash. We see this hash, and we know that we should use bcrypt, that we should do 2 to the power of 8 of iterations. We know the salt by encoding this. And when we run bcrypt, it should result with the hash. So that's how we verify if it's correct. Okay, so now I would like to show you some coding live demo of hashing speed comparison of MD5 and bcrypt. So that's a simple test only for convenience. So what we'll do here is we will hash a password. Let's say OWASP Meetup will be our password using MD5, using bcrypt with a cost factor of 8, cost factor of 10, a cost factor of 12. What we will then do is compare the times of these algorithms. Basically, the most important thing for us would be how many hashes can we do on my computer per second of each every one of those. What I'm using here underneath are basically bouncy castle implementations of MD5 and OpenBSD bcrypt. And this is also an important information. Don't ever really think about implementing your own crypto. Just use well-known sources. And I would say Bouncy Castle is one of them. Maybe not easiest to use, but once you figure out how to use them, you will be okay. So okay, let's run this and see what results we get. Okay, this will take a little bit of time. Okay, we have some results. First of all, I would like to ask you, for MD5, we have, every time we have the same result. For bcrypt, we have different results every time. Why is that? Yep. Thanks. Great answer. Different salts, because actually for MD5 I'm not using a salt, but if I was using the same, it would be the same. But as I already said, slow hashing algorithms are designed to provide salt by their definition, while for MD5 you to think about it, you have to know about it. They already have this in there, and we're actually generating a random string every time. No, it's not taken from algorithm itself, but you are required to provide it for the computation of hash. So there's a field right in the API. Salt is here, right? Just give me a salt, and usually it's some kind of a random string that's generated on our side. And what's important here are these average are these hashes per second. So we have, well, let's say almost 2,000. 1,784 hashes per second for MD5. For bcrypt with a cost parameter of 8, we have 41 hashes per second. And for the slowest, we have 3. So we see how it goes, right? It goes exponentially, of course, but we see how difficult it is, how long it takes for a possible attacker to potential attacker to compute all the hashes and crack the whole database, right? The only thing we gain here actually is time for us to react, because, well, he or she already has the database of hashes. We're pretty much doomed, but we're safe as we could be, because it will take really a long time for him or her to actually gain the passwords. So this is what we get. We get the time to react, to inform our users, to tell them, please change your password. If you're using the same password in other places, please don't. But if you do, just change them. A lot of time that we gain here. So that's the biggest advantage here. Okay, if you'd like, of course, it is available, and the source code of this is available on GitHub. Okay, another thing. How long does it take to compute a hash? Different approach. I found this really interesting article. This guy actually built a password cracking rig. The date of the article is pretty much half a year old. This article is pretty much half a year old. Pretty recent, I would say. So he built, we called it a budget cracking rig with 4 GPUs, as probably all of you know. GPUs are better than CPUs in cracking, but is $5,000 really a budget? I don't know, maybe for him. But basically, I think that if someone is dealing with crime professionally, if you can say that, then I guess $5,000 is not that big of a cost. He used this benchmark hashcat, and the results are the most interesting part. MD5, that's 19 billion hashes per second per GPU. It is 4 GPUs actually. So if you multiply that by 4, you get almost 80 billion hashes computed in a second. So you now know that if any MD5 hashed passwords leak, they are pretty much open, right? It's easy to crack. SHA-1, a little bit better, 3 times actually, around 3 times, but still, those are billions. bcrypt with the cost parameter of 5, which is actually pretty low for today's standards. We have almost 11,000. So by the comparison of these figures, you can, I think, if anything can convince you to consider slow hashing algorithm, it's that figure. So it's a really big advantage for us. Okay, migration process. Now I'll jump to the case study. So what we dealt with, what we did. Firstly, just for you to know the ecosystem that we're in. Ocado Technology actually is in the grocery business, and we have this web app, and basically this is what I will talk about. This is the www.ocado.com grocery online supermarket, which serves, which has basically hundreds of thousands of customers. We also have other stuff. We also have automation. We have warehouses. We have routing, but we'll focus on the website and the customer passwords. Okay, what we dealt with in the beginning. So our application, when I started developing, already used bcrypt with cost factor of 8. So having said what I said already, seems that it's already good, right? What was else there? Some old customers still had MD5, but not pure MD5. Back in the beginning, we were using MD5s, but when we firstly migrated to bcrypt, we did this. We just bcrypted the MD5s, so we had actually we were pretty safe. What it looked like in the database, actually, we had these where we keep the password hashes. We have a customer number, we have a password hash as a bcrypt hash. You already know this format I told you a little bit about. And we kept the password hash type. So if this user decides to log in, we are looking up the hash, and we are looking up the hash type. So if we see the MD5, we firstly calculate the MD5, and then we calculate the bcrypt from the resulting MD5 hash. And that's what we compare with. The other situation is simpler. So the customer can also have a simple bcrypt password. We have a hash type of bcrypt, and we only just bcrypt the password that we get and verify. So that's simpler. Okay. So why did we decide to change? Because we did the migration, right? So why? We have an information security team, and they were monitoring. They were asking us questions. Hey guys, what kind of algorithm are you using? Is it enough for us? So what I haven't already said is that with slow hashing algorithms, we need to balance two things. One is our safety, as I said, the speed of hashing, but two is what user experiences. So if it takes too long for user to log in, that we lose the customer, right? We don't want to let them wait too much, but still we don't want them to we want them to be safe, and we want our passwords to be safe. So we would like them to be as slow as to take as long as possible. So we have to balance these two. Okay, so we did some tests, and at that point, bcrypt with the cost parameter of 8 on our machines took around 80 milliseconds to compute, pretty fast. So we did a comparison to see, can we go higher and increase our safety? And having these figures, we decided that an average of half a second is something that every customer will probably won't even notice, but it will increase our safety, well, pretty much, right? So we decided, okay, bcrypt with a power of 12 looks cool. But back then, recently, application security team was formed. Actually, some members of this team are with us now here. So yeah, these guys. So in my team, we decided, maybe we'll talk this through with them. Maybe they have some tools. Maybe they have some, I don't know, maybe considerations, maybe suggestions how we should do it. And we talked with them, and they decided that they want to be a part of this, and they can provide something for us to make it easier for us. So there's this thing called crypto lib that we're using internally, and AppSec provides us with a password hasher API. It takes care of password hashing, so it has already it is already configured in a best way that we know, with by guys who know what they're doing, right? Who know their stuff, and we can use it as a black box. Just invoke password hasher hash, and we have a safe password. So it uses a well-known and safe crypto implementations. Underneath, it produces something called a hash vector that acts as a password hash. I will talk a little bit more about it later. And once we migrate to this new API, it is controlled by application security team since then. So we don't need to really, as developers, that we have also other tasks. We don't need to monitor it. We are now controlled by the best guys to do it. So we have just profits from it. Okay, now what's this hash vector I was talking about? So hash vector is a way to express what steps should I take to compute a hash. So this is an example of a pretty complicated and long hash vector, but I will go through it step by step to tell you what's cooking there. So we have a first element is a name of a hasher. So it pretty much says, okay, firstly, you will need to MD5 the input. Then you have a separator, and then we have salt that we need to use with the MD5. It's base 64 encoded. And we have this element. We have a separator of algorithms. So what then? Then we need to use bcrypt. What kind of bcrypt? Then there is this element of that we already know, the beginning of a bcrypt openbsd hash. So we already know that we need to use the cost factor of 8. We have the salt. So we're computing the hash of this hash that we already computed, right? So we're hashing the hash here. Then next algorithm. And this is the algorithm that actually is chosen to be the best one by application security. And this is PBKDF2, which is configured by not only defining the cost factor, but also the algorithm that is underneath. So it's SHA-256 used underneath with 250,000 iterations of it. And this is the salt that we should use. Then we have algorithm separator and the resulting hash. So we do all these 3 iterations. We hash, then we hash the hash, then we hash the hash, and we check whether the result is this. So that's how the hash vector is done. So you're asking if this is what the format of it is for? No, it's this is just a convenient way to express what we already have. As I already said, so we had some customers had MD5 hashed with bcrypt, right? And we would like to strengthen our hashes. So if we'd like to add another layer, so hash it with a best algorithm, right? We can express it in this way, in a convenient way, like universal way for a hash vector to, this is just means to express a hash in our database without any additional columns or anything. It carries all the information you need to compute a hash. That's all, actually. This is the developer convenience. So this is the API that password hasher provides. It has 3 methods: hash, verify, and migrate. A little bit about every single one of them. So hash is a simple method that you just provide a password. That's a new password. Let's say user is registering and providing a new password, and he says, okay, let Ocado be my password. And we invoke password hasher hash Ocado. And what we get is the best algorithm that AppSec decided to choose here. So it's PBKDF2 with the parameters they already gave you. And this is a short hash vector, the best algorithm, only that we need. The next method is actually verify. And this is the situation where customer is logging in. So we provide to this method 2 things: input password and the hash vector that we have in the database. What's interesting here is that what's the result of this method is verification result, which is a class, which is an interface that has 2 fields: is success and get hash vector. If the verification fails, we have is success returning false, and that's it. So that's an invalid password. If the verification is okay, so if the password is okay, then is success returns true. And the interesting part is the get hash vector. So it will be null if the hash vector is the newest best algorithm. But if somehow user has old version of algorithm, some not most up to date, it will already contain the best hash vector, and we can actually use this output to update the hash in the database. So we already know that the password is correct with the old hash vector, but we can replace it with a new safer one. It's very convenient. And the third method is migrate. So basically, if we have this situation that I already explained, the before state, so we have the MD5 and the bcrypt, and we would like to add the PBKDF2 strongest element, we use this method, and we get the password hash, the hash vector that contains the third element, PBKDF2 hasher, and we can replace the hash with a safer one. Okay, so what was the plan to migrate? What's the first thing that you think about when you, okay, I would like to change password hashes to stronger ones. When would you change them? Any ideas? Changes his password, right? So provides, when he provides the password. What if he logs in? So when he logs in and the old hash is correct, right? We can rehash the password that he provided because it's a correct one and replace it with a new one, right? So that's the first thing that we will use. So when customer logs in, we can replace it with a new hash, and also when customer changes his password. But not all the users will are logging in permanently and every day. So we would also like to asynchronously raise the security of our password hashes. So we will create these background jobs. Firstly, we will translate existing hashes, the pure bcrypt hashes, to the form of hash vector for the password hashes hasher to understand them, to have concise, coherent interface. Then we will use the migrate method of password hasher that will add the best element, the PBKDF2, to it and make our hashes safer, because you're as safe as the strongest algorithm that you're using. Okay, so and then we'll perform some cleanup. That was our plan. Okay, so what about migrating passwords when customers provide them? This is a simple scenario. Customer provides password. We're computing the old hash that we already have. If they match, if they don't match, that's an easy peasy thing. We just show them an error page, right? But if the passwords match, we can compute the hash vector and store it in the database. And if it's a password change, so if it's not something like user registration, but user actually changes the password, very important thing to remember in the process of transition is to modify also the old hash, because people make mistakes. There should also always be a possibility to back out. So we need the old hashes to be coherent with the passwords that user set, right? So we need to modify the old hashes. Okay, so first part of the asynchronous process is translating the passwords to hash vectors. So we added 2 columns to the to our database. That's actually hash vector and migration status. And by default, every password hash has a null hash vector and migration status of none. When we run the job on the existing hashes for MD5, we translate the existing hash to the form of hash vector. So this is a basic operation on strings because we have all the data. We have salts, we have algorithms, and we have resulting hash. So we're basically setting this migration status to translate it and adding and putting the hash vector in. For bcrypt passwords is a little bit easier because there's only one element bcrypt hasher of a hash vector, and we set also the migration status to translated. And another step that we took was actually upgrading these translated passwords using the migrate method of password hashers. So we added to all of the hash vectors that we created, we added this pbkdf2 hasher elements, as well as for the MD5 as well as for the bcrypt hashes. Okay, so we have this. And after full migration is done, after every single password we have a valid hash vector for, we decided to drop the old hashes. It's a very important part of the process, because actually we are as safe as our weakest hash here. So if we left the old hashes, it would get no use to the right. It would be just stupid to do it. So we need to drop the old data. And for the whole process, we generated some kind of a report for us, and it took some time to migrate all the passwords. So every now and then we were invoking some endpoint that generated this report for us. We've seen how many passwords hashes are in what state, and this gave us some information. We also have here this failure count, which is conveniently 0 here, but it's here to indicate that anything went wrong. Anything could go wrong with some kind of process. We can lose connection to the database. User could, I don't know, maybe update the password while we were dealing with the password. So fortunately, not really a lot of these failures happened. I think in production they did not happen at all. In our test environment, some, but for different reasons. But yeah, so we had this means to monitor the process. Very important thing. Okay, and this wouldn't be a complete case study without problems, and we had problems, of course. So first problem was time. So we computed how much would it take to translate password hashes and upgrade them, and the result was actually it will take us 30 days. So pretty long process. And what we decided to do with it was we would like to minimize the negative impact on user experience, right? We don't want to throw too much computation on the application nodes and result in slower response times and bigger response times. So we decided to add another node of our application to the load balancer, but actually disable it on the load balancer so it doesn't serve traffic for customers. And on this single node disconnected from load balancer, we did all the background asynchronous computations. And after the migration process, we decided to leave this node and service for it to serve content for users. So this is how we dealt with it. Another problem. We found out that actually a quite big number of passwords are orphans. That means they don't have owners. And it was really strange. So we decided to dig in, because there's no need to compute hashes for passwords that don't have owners, right? So we decided to discover the root cause. So it turned out that our process that we have automated process in production. There's a process that registers a new user every minute, every 2 minutes. And it has a cleanup process afterwards. And this cleanup process was missing one important part: delete password. So every day we were getting a lot of new orphan password entries. So we decided to firstly fix this problem, deploy it to production, test if it worked. Fortunately, it did, and then remove these orphans. But we're in IT; it's enterprise. Are we really sure that these are orphans? I mean, we were, but still, we had to have this possibility of back out. We cannot we cannot cope with a situation where someone loses his password, right? So we need to back it up. And for backups, we have DBAs, right? database has some backups. So I actually asked DBAs, how long would it take for us to recover a backup, a database backup? So it took so long that we decided, like restoring whole database is a costly process, and we decided we cannot go with this. So what we actually did was create another table that is actually a clone of the customer password table, where we put all the orphans. And after some time, when we decided, okay, this works, these are really orphans, we just dropped the table. This was a backup on our on our terms and by us. So this is how we coped with it. Another problem: entire process took over a year. A lot of time. Why? Well, actually, at some point when we started the migration, our application discovered some performance issues, and guys that were investigating the root cause asked us, hey guys, we have this process running in the background and this is your process, can you tell us, can you please turn it off, because we're investigating it and we're trying to deal with it. So we stopped the process. It wasn't us who were causing these issues, but all of this like we lost, I think, I don't know, maybe two weeks or a month from the time that we could use for migrating. But also year was actually the whole time discussing with application security, finding out the best algorithm, removing orphans. A lot of stuff happened, and also it wasn't really the highest priority task. Everything was, there were times that more important stuff had to be done. So that's how it was. That's why it took over a year. And I'm almost done. So I would like to leave you with some bullet points. I would like to encourage you to use slow hashing algorithms for passwords. I think I tried to convince you that they're way to go. What you need to do, though, when you use those is monitor the time taken to compute a hash, because the computer architectures move forward. They're faster and faster, and from time to time, it's a good idea to check whether the cost of our slow hashing algorithm is enough for today's time, right? And we need to reconfigure if it's needed. And hash migration, if you have an existing database of hashes, is possible. It's a little bit complicated, but good preparation is key. Very important thing is cleanup. As I already said, you need to remove old hashes. And it's a very important thing also to monitor the process. What goes wrong, if anything, we need to know to have this information. So yeah, I would like to leave it with you. A bunch of links for you. Some of the stuff I took from the password storage cheat sheet, as I said already, the sequence of slow hashing algorithms, for example, a good read. Password hashing competitions. What's really interesting here is, maybe you've heard about the Have I Been Pwned.com website. It's run by I think one of the most known security researchers, Troy Hunt, and he uses publicly available data breaches data and provides it for users to check whether, for example, your email has leaked in any of data breaches. It's usually I would not encourage you to put your email in some custom some custom website, but this is a legit one, and it has a very nice tab also, and a very nice API for passwords, for leaked passwords. And you can check whether your password has leaked anywhere. And that also seems fishy, right? Send your password to some guy and he'll say, yeah, your password just leaked. But actually, the newest API that Troy Hunt provides, version 2, is very neat. So what you do is you take your password, calculate SHA-1 hash of it, and send only first 5 characters to it, and you receive all the hashes that match the prefix. And you can check whether any of the hashes that are returned are your password. So it's a safe way to check whether your password leaked. Really nice stuff. Hey, that's it. If you have any questions, that's the good time to ask them.
Please raise your hand and I'll give you a mic if you have a question.
Maybe a stupid question. Why you have you had the hashes MD5? Why you didn't break the MD5 back so you could retrieve? Because you said it's quite easy to retrieve the password from MD5. Why you kept MD5 and hashed with the bcrypt instead of just breaking the passwords back?
So you would you are asking why didn't we crack our own database? I think that for like reasons that we aren't allowed to know the passwords actually. This is also a kind of contract between our users and us. Okay, we receive the password, right? But it's not really ethical to know the passwords. We didn't want to actually do it, and I think it from the software development and security perspective, it just seemed better to do it. I don't know, Mateusz, if you have any other comments here. Yeah, but we need to. Yeah, that's yeah. So we would need to crack them. So we would need to have some kind of a. Yeah, of course. Yeah. We would need to have some kind of a database to run through, right? Whatever, act like an attacker, basically, right? Another question.
Which, sorry, I just comment as well. This isn't really a problem, but it's pointless. It would be wasted effort, computing time, and so on from our part.
Faster would be just to recompute the hash, add another layer.
Exactly. Right? I mean, you can break MD5s, and this is pretty easy, but it's not that easy. You can do this in like 5 minutes. So it would be just waste computing time on our servers, and it's pointless.
Another question?
Have your database ever leaked? So
no.
I know that you are prepared.
Not that we know of, but no.
You don't know. Okay, no. That's good.
No. The approved answer to this question is tomato.
Tomato. Okay. Avocado.
I have one question. How did you handle the inactive users? I mean, the users that were active 1 year ago, but they are no longer your clients and they no longer log in. You cannot, know the password.
Yeah. So that were the asynchronous jobs that I've.
So they were translated.
Yeah, of course. All of them went through the migration. So.
Okay. So the second password, if this user appears that he's active, if his password will be upgraded.
Yes.
Okay.
Yes, so we have this very long hash vector with MD5, bcrypt, and pbkdf2. First time this user logs in and we prove that this password matches, we shorten it to the shortest because it's basically the safest. The safety is the same, and we have shorter stuff. So yeah, we're updating it.
So to crack your hash, I need to know algorithm. I need to know salt.
Yeah.
And it's actually stored in one place.
Yes.
And the only protection is
yes.
how hard you need to calculate and how much time you need. But what if distribute this piece of information in different types of storage?
So you're saying that maybe we should keep salt in other places?
Yes, as well as cost factor.
Yeah. So basically, salt by its definition, its only purpose it's to protect the rainbow table attacks. So it should be out in the open. The thing that you maybe need here is pepper, which is a different thing. And pepper is something that you can store like in hardware or in some secret storage that is taken from a different place to like increase your security. You can do that. We are not using pepper. And for the cost factor is basically the same. we didn't want to achieve like we didn't want to use the pattern of security by obscurity. We wanted to just have all this information in one place, and we believe, and basically all of the cryptography world, I think, Mateusz, right, believes that that's enough for us for now, right? To keep it seems that we have all the information in the open, but the time taken to crack is something that is safe enough for us.
So I'll add to that the general rule of modern cryptography, I don't remember the name, but the rule is that the security,
something like that.
The security of your cryptography can depend on secrecy of algorithms. So you need to trust your algorithms, and you need to trust your process enough so you can put everything in the open and be sure that you are still secure. This also relates to like encryption with public or private keys, and
there is an assumption that if someone gained control of our database, it's very highly possible that this person also has our source code. So we lose all the information, just so he already has it. That's the assumption that you have, that everyone takes, I think, with the breaches. So yeah.
How have you handled passwords stored in the database backups?
So what would we?
Yes, because you make a backup of database and store the old version of that password before you dropped the MD5 column. But the attacker can restore the database from the backup.
Yeah, but backups are not kept forever, right?
Okay. So have you dropped all the backups? Successful migration.
That's a process that is automatic, right? So all the backups are. I don't know how long they are kept because I'm not a DBA, but we left it to the DBAs, right? So we followed. We didn't tell them, you need to drop the backups, because there may be some issues with the application that are so severe that we need to go back to the version which does not support hash vector. So so basically the process was the same as it is day to day.
Okay.
Thanks.
It seems that the biggest challenge was to it seems that the biggest challenge was to hold these hash vector functions and procedures, and this code which is just working, and you have already done this, and you checked if this working on the production, So maybe you will consider to open source or open this code just to make the world better.
That's actually a question to AppSec, because the most part of it is the password hasher, and I think that the cryptolib also contains a lot of other stuff. But basically, what I wanted to show here is the concept. It's not that I think it's not that complicated for any other company to adopt for now, but your question still remains valid. So I don't know if there are any plans of open sourcing. I don't know of any.
There were ideas. Nothing is decided yet. That's unfortunately all I can say right now. We are thinking about it.
Okay, another question.
I don't know how many logins do you have daily for your application.
Okay.
But did you notice any changes in application performance after the change?
Not really. We were before we actually did it. We checked how much of processor is used during logins, and no, it wasn't a significant impact at all. Actually, there's not that much logins, or maybe our machines are that good, right? But we didn't actually experience any peaks in traffic or whatever in the CPU usage.
The database you use is relation.
Yep, relation
with because
I know. Okay,
you have a relation with primary key and foreign key, and this way you could get rid of orphan password, because it would be forbidden to remove.
I know, but we're living in microservice world, right? Where we have separation of concerns, and these two concepts do not really play with each other that well. So having that there's a separate service that cares of passwords, this is why this appeared, right?
Did any user notice that the login process is half second longer?
No, we haven't. We haven't heard anything about this from anyone. So there's also a lot of other stuff that is going on during login. So it's also reduced this, but no, we haven't heard any complaints so far.
Hi, how have you taken care of the race condition problem when you run the asynchronous job in the background, and let's say a user changed the password, and you hit the problem where you probably had something going on, and the password and the hash vector changed. So how you deal with it?
Yeah, that I've shown you this report, this small table, right, with failure count. This would actually when before we are updating the hash vectors, we are actually checking also if it is the state that we suppose it should be. If it wasn't, we increased the failure count and we left it as is, and the next run of the job would try again. Any other questions? Okay. Thanks for listening. And thank you. I think now we'll have a half an hour break, right?
Yeah, it was supposed to be half an hour.
Okay.
But we're a little bit behind the schedule, so maybe 20 minutes. So
in 20 minutes, your presentation.
Yep.
Cool.
7:40 p.m. more or less.